Let's start chapter 6. This is section 6.1. We're going to talk about inverse functions. Okay, let's go back a bit to the idea of what was a function. A function was a mapping from a set domain to another set range. And here's the function f. And you give an input in the domain like 1, you'll expect an output like 3. With some property that for one input you expect at most one output, not more than that. If you pick another output, you can go to the same input 3. If you pick another input 2, then you can go to the same output 3. But the other way around is not possible. For example, 1 cannot have 2 different y values. This is not correct. This is not going to be a function. Okay, so here, for example, f of 1 would be 3 as well as f of 2. They both are equal to 3. It's a well-defined function. What does an inverse function do? Inverse function says, okay, what if I write this set the other way? What if I give you the y value and ask you what is the original x value? Can you answer these questions? Can we go backward and find out what was the original x values? So given the y coordinate, we figure out what is the x coordinate. This is the question. And notation for it is f negative. F negative 1, just that negative 1 is not an exponent. This is just a notation to represent inverse of f. It's not the same as 1 divided by f. It is not the same as this. These two are not equal to each other. This is just a notation to represent the inverse function. Okay. So what does the inverse function do? You give it the y value, and it goes back and gives you the original x value. But to be a function, for every input, you should expect one output, not more than that. And if you notice here, we have multiple outputs, 1 and 2. Given x value of 3, we got 2 different y values. So this would not be a function. It's an inverse operation, but it's not a function since you have one input and given 2 outputs. So to have an inverse function, the original function should satisfy a certain property. And that property is what we call it the one-to-one property. And what it means is if you pick an x value, or let's say 1, 2, 3, they all go to different y values. So for every x value, you have exactly one y value, and all those y values are different from each other. So this is maybe 2, this is 5, this is 8. You do not have the option to go to the same y value. This is a function, and if it satisfies this property that every x value has different y value, it means this is a one-to-one function. Why are we mentioning this? Because now if you change the arrow direction, so let's say this is f, if I change the arrow direction, starting from the y values, and go back to the other side, this would be the inverse function. And you notice that every input, these are the input now. What we expect is one output, not more than that. And this means you have an inverse as a function. The inverse satisfies the property that one input gives you one output. And what can you answer is if, for example, if you know f of 1 is 2, here in this case, if I pick x value of 1, y value is 2, for the inverse, what do we know is that if you give me the y value, for example, 2, means this is given the y value, what do I expect is the original x value must be 1. The relation between the inverse and the original function is basically that the y and x values are reversed. So here, for example, if I know f of 3 is 8, what do I know about the inverse function? I know that the inverse of 8, if I give you the y value, you should tell me that the x value was 3. The input of the inverse function is basically the y value. What do you expect as the x value? And here the input is x. What do you expect? The output is y for the original function f. And if you do composition, if you compose these two together, for example, if I ask you what is f inverse of f of 3, what do we get? F of 3, we know it is 8. So we get f inverse of 8. And what is f inverse of 8? F inverse of 8 is 3. So whatever you start with, you'll end up with the same thing. Because it means I ask you what is f of 1, you'll tell me it's 2, for example. And I ask you what is f inverse of 2, you'll go back and tell me this is 1. If you do composition, you always go back to the original value. These are all could be explained through a theorem that we're going to mention later. But I just wanted to mention it now so we don't have to come back and rewrite these stuff. So definition of a one-to-one function. A function f is one-to-one if it never takes the same y value twice. So that means all the y values are different. If you give it a different x value, if you pick two different x values, what do you expect is corresponding y values must be different. They do not equal to each other. And you can check that through a horizontal line test. Vertical line test would give you a function. Horizontal line test will tell you if the function is one-to-one. So to see if you have a one-to-one function, for example, here are two examples I already have here. X squared and x cubed. Compare these two functions. Here is x squared. Here is x cubed. These are two different functions. One is, and it looks like this. This is x cubed. The other one is x squared. Okay. Think about this idea that if I ask you what is f of 1, and by the way, this is f, the other one is called the h. F of 1 would be 1 squared, which would be 1. How about f of negative 1? That would be negative 1 squared, which would be simply 1 again. So therefore, at 1 and negative 1 have the same y value. So if this function had an inverse, and if I asked you what is f inverse of 1, means if I give you this y value, can you tell me what is the original x value? Tell me there are two original x values, 1 and negative 1. But that means this could not be a function because it gives you two different outputs. And this could be checked through this property that if you draw a horizontal line and crosses the function more than once, means there are 2 points with the same y value, different x values, but the same y value. That means this is not, it is a function, but not a one-to-one function. By the way, this 1-1 is the same as 1-to-1, the same as this. So if they write it like that, it's a shorter way. It's not a one-to-one function. Which means if it's not a one-to-one function, you cannot talk about the inverse as a function. So all the inverse properties, you have to have a one-to-one function to talk about. On the other side, if I pick x cubed function, every x value that I pick, let's say 1, has a y value of 1. If I pick something else like negative 1, has different y value. Has different y value, which is negative 1. So every horizontal line that I draw, it crosses at most once. In this case, it's exactly crossing once. If a function passes the horizontal line test, it's a one-to-one function. And in this case, I can tell you the inverse function. It basically is the cube root. And this is nothing that you shouldn't expect. So if I give you that f of 2, sorry, not f, h. We call it the h function. If I tell you that h of 2 is 8, because 2 to the power 3 is 8, then you can tell me that the inverse of 8 must be 2. Because if I give you the y value, you should tell me the x value. And if you replace 8 here, cube root of 8 is simply 2. It's what we get as an inverse. So now our focus would be how to find this inverse function. Okay, so again, to talk about the inverse function, the original function have to have the property that it's a one-to-one. Otherwise, it's not possible to have an inverse as a function. And one important thing that you should notice is that if f is a function which is one-to-one with domain of A and range B, then the inverse starts from the B and goes to A. So which means the domain of the inverse must be B and the range would be A. And what does the inverse function do? Inverse function takes the y value and gives you the x value. The original function takes the x value, gives you the y value. And this should be true for all the y values in the range and the x values in the domain. This relation is true for both sides. One, if this is true, this must be correct as well, because they are consequence of each other. You define one based on the other. Okay, here's for example, given f of 2 as 3, and they ask you to find the f inverse. So if I ask you what is f inverse of 3, you'll be able to tell me that the inverse of 3, give me the y value, I'll give you the x value, which is 2. F inverse of 5, giving me the y value, the x value must be 3. F inverse of 0, given the y value, x value must be 7. And if they ask you what is f inverse of 7, the answer must be, we don't know. In this case, undefined, because there is no y value of 7. Unless you know that, for example, f of 5 is 7. Then in that case, you would say, okay, this is 5. The x value is 5. But if this is not given, then we don't know the f inverse. Okay, so this is certain properties of the f inverse. And how do we find? Oh, and this is what I mentioned earlier. The composition of f with f inverse always goes back to the original function. So for example, if you start, again, think about this. Let's say here, I'll pick an x value through f. F of x would be this y value. F inverse goes back. So if I start from x, for example, and say, what is f of x? You should say this is a y value. And if I take an inverse from this, means start from y, go inverse, and what you end up with is the original function x. So the inverse, f inverse of f of x is simply x. This is what we have as a property. The same, if you start from y and go with the inverse function, so f inverse of y, for example, this would be x. It gives you the x value. And if you take an f from that, so f of x would be y. If you ignore this notation, it's just what we have here. Why am I mentioning this? Is it makes the work easier sometimes to check if you have an inverse function. For example, if you're given something like x cubed as f of x, and they say, for example, f inverse g. Let's say g of x is given as cube root of x. And they ask you, are these two inverses of each other? What you need to check is these two properties. See if they satisfy that. That means find out the composition of f of g of x to see if this equals to x, and g of f of x to see if this equals to x. Whatever you start with, you should end up with the same thing. And by the way, I call them both x. You can call one y, the other one x, but it doesn't really matter. So in this case, what is f of g of x? It would be f of g of x is given cube root of x. Then cube root of x goes into the f function. It should be cube root of x to the third power, and that simplifies to x. The other way around as well. It would be g of f of x is x cubed. G of that would be take a cube root of x cubed, and that is simply x. You notice that both combinations give you the original function and the original value x. If you start from x, you end up with x. If you start with y, you'll end up with y. Okay, which means this is true that these two are inverses of each other. You can say G is the same as F inverse. Or you can say F is the same as G inverse, either way. Okay, so now the question becomes how to find these inverse. If you're given x cubed, how do I find the F inverse? And the idea would be to follow 3 steps, 3 simple steps. But before you follow the steps, you have to make sure that F is 1-to-1. And you can always check that through horizontal line test. Replace, so step 1, replace F with Y. If you're given the function F, replace it with Y. Step 2 would be solve in terms of X. Normally you have the function in terms of Y. You say Y equals to something in terms of X. This time you solve X in terms of Y. You write X equals to something in terms of Y. Then at the end, for having notation everything based on X, interchange X and Y. And that would be our inverse function. An inverse function, normally you should say if it's inverse of Y, but as a function we expect the X value to be our variables. So we write this X and Y interchanges to write the functions as a function of X. Like this cube root, we could have write cube root of Y, but we should have mentioned that this is G of Y equals cube root of Y. But you can always call the variable X. Normally, if you call it as a function, use X as a variable. That's why we interchange that X and Y at the end. Here's an example of it. Given the function F, this is a line 2x minus 5. This is this line. It always passes horizontal line test. So it has an inverse. So it means if I go through these steps, I'll expect a unique result. Otherwise, if it's not a 1-to-1, you are not going to get a unique result. At some point, there would be a plus or minus if you take a square root somewhere. So step 1, replace f of x with y equals 2x minus 5. Step 2, solve for y, solve for x. So I'll add 5 to x, divide both sides by 2. So x would be y plus 5 divided by 2. Step 3, just interchange x and y everywhere. Every time you see x, replace y. Every time you see y, replace x. Plus 5 divided by 2. Now this is basically the inverse function. So I can say f inverse of x is x plus 5 divided by 2. And you notice why we changed the x and y is just to write it in terms of x. Otherwise, you should say f inverse of y equals to that. But to avoid that, we always interchange x and y. And that's their inverse function. You can check it to see if it's correct. For example, if I ask you what is f of 0, you say replace 0 into the function. What you get is 2 times 0 minus 5, you get negative 5. So in the other case, if I calculate f of negative 5, f inverse of negative 5, it should give me 0. Give me the original value, x value. Let's try that. What you get is negative 5 plus 5 divided by 2. Just simply 0. Means at least it works in this case. And if you check any other points, it would be true. You can check generally by calculating that composition, these two, to see if that's the correct inverse. Here's another example. So let's do it step by step. Find the inverse function. We're trying to find out what is f inverse of x. Okay, so y equal x cubed minus 2. Add 2 to both sides. Y plus 2 equals x cubed. Take a cube root. X would be cube root of x plus y plus 2. So therefore, what is the inverse function? We change the x and y. I can say f inverse of x is cube root of x plus 2. Again, you can always check through the composition, but the fast way would be to just test the number. What is f of 0? It would be negative 2. 0 cubed minus 2. What would be f inverse of 2? It would be negative 2. Plus -2 into the function, you get the cube root of -2 plus 2, which is simply 0. Gives us the original x value. Okay, one last thing to mention about the inverse functions. The definition is the graphing. Graphing of f inverse is not difficult. If you graph the original function, there is a relation between f and f inverse. So here, let me show you through this, maybe a bunch of points. So let's say if you know f of 1 is 2, f of 3 is given 4, f of 5 is given 0. And I ask you, what is the f inverse look like? You should know certain points, at least the f inverse. F inverse of 2, 4, and 0. We should know these, because f inverse of 2 would be corresponding 1, f inverse of 4 would be corresponding x value of 3, and the other side would be 5. So now, if I graph the f function, how does the f function look like? The original f function would be at 1, you would have 1 and 2. 1 and 2, this is a point. Have 3 and 4, say 4 is here. And f of 5 would be 0. 5 and 0. These 3 points are the corresponding points correspond to f. How about inverse? At 2, we should have one value, y value of 1. So f of 2 must be 1. F of 4 must be 3. At 4, we have 3. And at 0, we should have 5. 0 and 5. And what you notice is this point moved here, this point moved there, and basically I can tell you that they're symmetric about this line y equal to x. Every point changes symmetrically about that line. Because basically you're changing x and y location. The symmetry through that would be interchanging x and y would be symmetry through this line y equal to x. So if you know the graph of f, let's say we knew graph of f as x cubed, so 1-to-1 function. So here is x cubed. Change this to red. F of x is given x cubed. How would the graph of the inverse, which is cube root of x, looks like? Is draw this symmetrically about this line, 45-degree angle line. And what you get is basically this kind of curve. If you reflect the red curve about that 45-degree angle line, what you get is basically this inverse function. And that is basically the graph of the function. So if you want to graph an inverse, maybe graph the original function, then reflect it. Or if you can find the function, you can just pick points and draw it. Okay, so graphing inverse is not difficult. It's just a reflection about the y equal to x axis. Y equal to x line. And here's one main theorem, which is related to the derivative. The proof is kind of simple through the chain rule, but I want to avoid it. You can check out the proof. F inverse of x. We know this already is x. This is basically a hint to the proof. This composition, we already know it's x. We take a derivative from both sides. What do you get? Derivative of this? It's 1. Derivative of the other side, we have to apply chain rule. F derivative of f inverse of x multiply by the derivative of the inside. F inverse derivative of x multiply by the derivative of x, which is simply 1. So if you want to find out this term, the derivative, which is the inverse function derivative, divide both sides by that. So what you get is this theorem. The inverse function's derivative is basically 1 divided by the derivative of f evaluated at f inverse of x. This is the main theorem to calculate derivative of f inverse function if you don't have the f inverse function. If you have the f inverse function, you can already find the derivative. For example, if I know that inverse function is that, I can tell you that the inverse f inverse derivative of x is basically, I can write this as x to the power 1/3 and take a derivative. It would be 1/3 x to the power negative 2/3. I don't need to do anything. This is it. But if I don't know the derivative, if I don't know the inverse function, the formula for that, then I can use this theorem. Okay, so here's an example of it. Given function f as 2x plus sine x, find the inverse. It's kind of difficult to find the f inverse function. This is kind of complicated. It's not that easy to find. You can try it, but it's not easy to find because there are two terms depending on x, and solving for x is not that simple. So what we can do is use this theorem, because we want to find out two things. One is f inverse at 1, then the derivative at 1, then f inverse derivative at 1. So first, let's figure out this f inverse of 1. What does f inverse of 1 means? That means if I give you the y value, can you tell me what is the x value? This is basically all trying to figure out. So if I tell you the y value, means given the original function's y value is a 1, find out what is the x value. So you're given 1 equals to 2x plus sine x. Can we guess what is the x value? You can try to guess. So this is not sine x. This is supposed to be cosine x. Sorry about that. Cosine x. There we go. Not always that easy, but so normally in these cases, solving is not an option. Is you have a linear with a trigonometric function, solving is not that easy. So what we can do is try to pick some numbers, random numbers, to see if they work. Something like 0, pi, pi half, any combination of those. Maybe 1, 2, negative 1. So let's start with 0. If I replace x with 0, does it work? 2 times 0 would be 0 plus cosine of 0. Is that equal to 1? And the answer is yes. That means I can figure out, I can tell you that the x value must be 0 to satisfy this equation. So therefore, I can guess that my inverse at 1 must be 0. And since they tell you that there is an inverse function, that means this was a 1-to-1 function, or we assume it's a 1-to-1, and we figure out the 1x value. The inverse function at 1 is 0. How about the derivative? I'm going to use this property that the derivative of the inverse function, at 1 is basically 1 divided by the derivative function, derivative of f at f inverse of 1. And we already figured out something. We figured out this inside. That's why I separated this two questions into two parts. We already figured out that f inverse of 1 is 0. So I can replace that with 0. So the question is simply 1 divided by the derivative is 0. The derivative of what? Derivative of the original function. This is the original function. So what is the derivative of that? F prime x would be 2 plus derivative of cosine is negative sine. 2 minus sine x. So now what would be the derivative at 0? 1 divided by 2 minus sine 0. Which is simply 1 over 2. So we found out the derivative of the inverse function at 1, and that is simply 1/2. Okay, so this is the derivative. Let's see if here there's another example. The idea is always the same. Given the function f, if you cannot find the f inverse, use this property. What is the f inverse derivative? They ask you for the derivative, you use that. Otherwise, you should simply find out what is the f inverse. So f inverse derivative at 3 means find out first what is f inverse of 3, because that is necessary. Then we use that formula that f prime, f inverse of 3 derivative is 1 divided by f prime of f inverse of 3. So I start with finding out what is this inside, then replace it in the derivative. So f inverse of 3, that means given the y value is 3, given this is 3, can you guess what is the x value? So 3 would equal x to the power 5 plus x to the power 3 plus x. And a simple guessing will tell you that if you pick x to be 1, you have 1 plus 1 plus 1. So therefore, I can tell you that the f inverse of 3 must be 1, that's x value. That satisfies the equation. So now the derivative at 1 is what we're looking for. Because this simplifies to 1 divided by f inverse, f prime of this inside, simply 1. So f prime x, what is f prime x? It is 5x to the 4th plus 3x squared plus 1. So what would be f prime of 1? 1 divided by 5 plus 3 plus 1. I replaced the 1 for x. And that is 1 over 9. So we found out the derivative for the inverse function evaluated at 3. Every other example are very similar to this, so I only use these two examples. Okay, it's important that to check if the function is 1-to-1 to find the inverse first. Without that, you may end up with two solutions, multiple solutions. Okay, so let me stop here. Next time we'll focus on exponential functions and logarithmic functions.